Hello, y'all. Unit 6, Day 2, Notes, Vectors, Part 2. Let's go. Now, if we were going to solve for cosine of theta using this diagram here as an example, here is angle theta. Remember, we would use adjacent over hypotenuse. Cosine follows that pattern. Remember, I wrote it down, but you couldn't see it. Cosine follows adjacent over hypotenuse. Well, here in this diagram, our adjacent is x, and our hypotenuse, that's the magnitude. Now here they want us to solve for x. So in order to do that, what we'd have to do in order to get x all by itself is we'd have to multiply both sides by the magnitude. That would leave us with x equals magnitude times cosine of theta. Over here, sine, that's the same thing, or at least we use this to help us out. So that's opposite over hypotenuse. Angle theta is here, opposite would be y. Hypotenuse is still magnitude. And if we were to follow that same pattern here as we did above, we would end up with y equals magnitude times sine of theta. We'll be using this process a lot today. So example 1, they want us to find the component form of the vector shown. So I'm going to start by drawing my little symbols there that stand for component vector. Okay, so our magnitude is 23. And angle theta is 40 degrees. Okay, so now what we're going to do is we're just going to follow this pattern up here that we just wrote down for cosine and sine. So we're going to start with our magnitude, right, cosine, and then 40 degrees, comma, and then repeat the pattern except put sine in there this time. Magnitude, sine, 40 degrees. Now we have it in component form, but we have it in a trig setup, a trig manner. So we want to get actual values here. So you're going to need your graphing calculators. And just input in your calculator what you have written down on your paper here. So we want to start with 23 cosine 40, enter. And then we're going to need to write that value down, round to 3 decimal places if it does not state otherwise. 17.619. And our sine value is going to be 14.784. We have now found the component form of the vector shown. Example 2, find the components of the vector with a direction angle 225 degrees in magnitude of 25. Magnitude 25, angle theta 225 degrees. Now we start plugging into our component form and we can solve this problem. Start with magnitude, cosine, angle. And now magnitude, sine, angle. And now input that into your graphing calculator to find your answer. Looks like negative 17.678. And again, the same answer. We have now found the components of the vector. Example 3, find the component form of the velocity vector for an airplane traveling at 200 miles per hour in a northwesterly direction, exactly halfway between north and west. I'm going to draw a little diagram for you. Okay, so this plane is traveling 200 miles per hour in a northwesterly direction, exactly halfway between north and west. So it's traveling this direction. Now we know that from one quadrant angle to another, it's 90 degrees of separation. So this is 90 degrees here. If we go all the way to our terminal ray here, that is exactly halfway between the quadrant angle, we know that is 45 degrees. So if we add those two values together, that will give us our angle theta, which is going to be 135 degrees. Magnitude, they're telling us that it's traveling at 200 miles per hour. And now we can plug into component form and then use our calculator. Magnitude, cosine, angle. Magnitude, sine, angle. Calculator time. Negative 141.421. Now let's go find our sine value. $141.421. And done. Example 4, the wind is blowing at 20 miles per hour at a bearing of north 30 degrees west. Express the velocity as a vector. Draw a coordinate plane once again. We haven't seen bearings in a while, so here's a review. If we have a bearing of north 30 degrees west, what that means is we start at the northernmost point of our coordinate plane. We travel in a 30-degree rotation towards the west. So right about maybe there. And then from the origin, we connect that plot. And that is our terminal ray. So this is the direction the wind is blowing. Now, here's what you need to remember. North 30 degrees west. 30 degrees is here. And from here to here is 90. Therefore, if we go from the positive x-axis all the way to the terminal ray, we would need to add 90 degrees and 30 degrees together to get our angle theta. We have a magnitude of velocity of 20 miles per hour. Let's plug this into component form. Magnitude, cosine, angle. Magnitude, sine, angle. Calculator time. Negative 10 for our cosine value. And 17.321 for our sine value. We have now expressed the velocity as a vector. Example 5, find the component form of the sum of u and v with direction angles theta subscript u and theta subscript v. At least I think that's how you say that, subscript. I don't really remember, but I think that's what it is. That's really not that important. But anyway, let's move on to what is important. So we have two sets of data here. We have a magnitude of 6 and an angle of 20 degrees. Here we have another set of data with a magnitude of 3 and an angle theta of 150 degrees. For right now, we are going to set up a component vector just using these 2 bits of information. So 6 cosine 20 degrees, 6 sine 20 degrees. Now what we're going to do is I'm going to set up another component vector now using this bit of information. So 3 cosine 150 3 sine 150. And what we're going to do is we are going to add these 2 component vectors together, and that's going to give us our resultant vector. Now here's how you want to add these together. Remember this cosine column, we want to add cosine with cosine because those are our x values. So add x values with x values, and then you're going to add your y values with y values, or sine with sine. So we're going to begin with 6 cosine 20. Make sure you close the parentheses there, plus 3 cosine 150. You get 3.040. Comma, now same process, except we're going to add our sine values together. So 6 sine 20, close parentheses, plus 3 sine 150, 3.552. We have now found the component form of the sum of u and v. That's your answer. Example 6, a plane is flying on a bearing of north 65 degrees east at 500 miles per hour. I'm going to stop there, and I'm going to start plotting down that information. So this plane is flying at a bearing of north 65 degrees east. So from the north, we're going to do about a 65-degree rotation towards the east. And then we're going to remember 65 degrees of rotation. That is this angle here, but we need this angle there. So we would need to do 90 minus 65 in order to get that angle, which would give us 25 degrees. So that's the angle theta that we're working with here. Our plane's velocity is 500 miles per hour. So let me go ahead and set up the component vector for our plane. Magnitude, cosine, angle. Magnitude, sine, angle. All right, now let's continue on with the rest of the problem. A tailwind that adds to the plane's velocity is blowing in the direction north 35 degrees east at 80 miles per hour. So let me diagram the wind. So from the north, 35-degree rotation towards the east. This is the 35-degree angle, but this is the angle that we actually have to use in order to solve this problem. So 90 degrees minus 35 degrees would give us 55 degrees. And the wind is blowing at 80 miles per hour. So now we can construct our component vector of the wind. Magnitude, cosine, theta, magnitude, sine, theta. Okay, let's now add cosines with cosines and then add your signs, and that is going to give you your resultant vector. (500) cosine 25 plus 80 cosine 55, or 99.040. Now let's add our sine values together. 500 sine 25, close the parentheses, plus 80 sine 55. 276.841. We now have a resultant vector, but wait, we are not done. No. Because now we have to express the actual velocity of the plane as a vector. Then, which we did, by the way, sorry, we just did that. But then we have to determine the actual speed and direction of the plane. Here's how we do it. With our resultant vector, that is our x value, that is our y value. If we're now going to determine the actual speed, what you're going to want to do is take the square root of your x value, but square it, and your y value, and square that. If you do that process, you're going to get your speed, your velocity, your magnitude, whatever word you want to use. So let's do that. Square root, open parentheses. Now we don't want to use our rounded values. We want to use the actual values that our calculator gave us originally. So I'm going to scroll up and find my x value, and then hit enter. Close parentheses, square, plus open parentheses. Let's now scroll up and find the y value, enter, close parentheses, square, and now enter. That is the speed's velocity. The speed's velocity, I meant the airplane's velocity, 570.686. 570.686 miles per hour. So there's answer 1. Answer 2. Now it wants for us to determine the direction of the plane. Here's how you're going to find direction. We still need to use the original numbers in our resultant vector, but we're going to use inverse tangent because that will help us find our direction. Y divided by x. That will give us our direction, or at least help us determine what our direction is. So let's do that. Second tangent. I'm going to scroll up and find my y value. Enter. Divided by the x value. (29.012). I'm sorry, 12. What am I thinking? 29.019 degrees. That's the direction the plane is now flying. Example 7. Small plane is flying at a speed of 180 miles per hour on a bearing of north 50 degrees east. A small plane is flying at a speed of 180 miles per hour at a bearing of north 50 degrees east. So from the north, 50 degrees of rotation towards the east. This is where the angle of 50 degrees resides, but we need this angle theta here, which would be 40 degrees. Our magnitude, our velocity is 180. I'm going to go ahead and build my component vector, magnitude, cosine, angle, magnitude, sine, angle. And this was for the plane. This is the component vector for the plane. The wind is blowing from west to east at 40 miles per hour. The wind is blowing. See if I can get a different colored marker here to demonstrate this. The wind is blowing. Here's the west to the east. That's the direction the wind is blowing. From west to east. Now, this terminal ray, it created an angle of 40 degrees. This terminal ray here is not rotating at all, 0 rotation. So this has an angle theta of 0 degrees. If it's pointed directly to the east, that's pointing to 0 angles of rotation, a 0-degree angle of rotation. Now this wind was blowing at 40 miles per hour. So now we can build a component vector for the wind. Magnitude, you don't need a degree symbol there, sorry. Magnitude of 40. Cosine 0. Magnitude sine 0. We now have to find the ground speed and direction of the plane. In order to do that, we have to figure out what is the resultant vector. So let's add cosines with cosines, sines with sines, and then we can begin to complete this problem. $177.888. And now let's add our sine with sine. 180 sine 40 plus 40 sine 0. 115.702. All right, we need to find the ground speed and direction of the plane. So we're going to follow the exact same process that we did with example 6. Square root, open parentheses. Now I'm going to scroll up and find my x value. Close parentheses, square. Our speed is traveling at our speed. I did it again. Did it together for us. Our plane is traveling at a speed of 212.205. And now for our direction. Inverse tangent y divided by x. Looks like 33.0 0.41 degrees. That one is now complete. And for example 8, guess what? We're doing the same exact thing that we did for examples 6 and 7. So I'm going to work this one out, but I'm going to do it silently. That way, if you would like to follow along, but try and do it on your own, I will not be interrupting your process.